In this lesson, we'll discuss exponential growth and decay and how that relates to calculus. To start with, just a little bit of notation, I'm going to let the letter P, or P of t, represent the amount of some object. And this could be population, the balance of a bank account, maybe grams of some radioactive substance, for example. So first, if I say P of 0, this is the amount of your object at time t is equal to 0. And we call this the initial amount. And we're going to denote that by P naught, or P sub 0. Now, what about the actual equation? So not just the initial amount. Since we're talking about exponential growth or decay, we'd like to use an exponential equation. So P of t is equal to some initial amount, which is P sub 0, times some number b to the power of t. This is an exponential equation because we have a base, a number, and a variable and an exponent. And if you think about it, if you put 0 in place of t, b to the 0 is 1, and it will leave you with your initial amount. For what we're doing in here, we can actually express every single exponential equation with one that has a base of e. So that is p sub 0 times e to the kt, where k is a constant. In fact, we call k the proportionality constant. Why are these two equations equivalent? It's due to this identity. E to the natural log of any number b is equal to b. E and the natural log are inverses, so they can cancel each other. So here, k, the proportionality constant, is equal to the natural log of b, some base. If you take k and substitute it with the natural log of b, you'll have e to the natural log of b, which just would give you b back. Now, how does this relate to calculus? What we're interested in is not just the equation, but the derivative of the equation, which is this. If p is the amount of some object, then dp dt is the rate at which the object grows or decays. So if the object was, let's say, a population, that'd be the rate at which the population is growing at some given time. If it was the balance in your bank account, it'd be dollars per year, how fast is your account growing, and so on. Now this brings us to a very important definition. We say P grows or decays proportional to its size or amount if dp dt is equal to k times p, where k is this proportionality constant. We call this equation here a differential equation. And we call it this because it's an equation that contains a derivative. So if something is growing or decaying proportional to its size, it means it must satisfy this equation here. And this is equivalent to exponential growth or decay. What I'm going to do is I'm going to take this equation and show that it satisfies this differential equation. So here's what I mean by that. If P of t is equal to P naught times e to the kt, and I plug this into this equation, it should make the left side equal the right side. Let's see. So dp dt, if I take the derivative of this thing, well, this is a number, and we have e to a power, and k is a number. Taking the derivative means I'll have to multiply the whole thing by k. So I get p naught e to the kt times k. So this number comes out by the chain rule. And I'll reorder this by putting the k in front. That's k times p naught e to the kt. And here I have k, and p is the same thing as p naught e to the kt, which means this is equal to k times p. This is the equation that satisfies this differential equation. And if we see this, this means exponential growth, or you're saying that some amount is growing or decaying proportional to its size. So there's only two options that we're going to encounter, either growth or decay. Something is either increasing or something is decreasing. So over here, this is obviously growth, and over here, this is decay. what is it about this equation that tells you if something is growing or decaying? And the thing that tells you is the proportionality constant. If your proportionality constant k is a positive number, like maybe k is equal to 2, that means your function will increase. Over here, if k takes on a negative number, it means that it will decrease. Let's try this in example 1. Suppose you invest $5,000 into an account that earns 4% interest compounded continuously. And what this means is it'll grow at a rate proportional to the amount of money in the account. Can we use this type of equation to determine how much money is in the account after 10 years? And also, how fast is the account growing at this time? To start with, we have to identify a few things. I want to use this equation to model this growth. And I can do that because we're told it grows proportional to its size. What's my initial amount? Well, that's going to be $5,000. That's our starting point, $5,000. So I'll plug that into the equation. That's 5,000 times e to the kt. I also need to know, well, what's the proportionality constant? How fast is this account growing? And in this case, that's given here by this percent. So k is equal to 4%, and as a decimal, that's 0.04. If we put this all together, we get this equation. This formula will tell you the amount of money in this account at any given time that you'd like. If you put 0 in place of t, this whole part's equal to 1, meaning it'll give you your initial amount of $5,000. But how much money is in the account after 10 years? To figure that out, we can take 10 and put that in place of time. And I'm going to get a number in my calculator. Okay, so I just typed this in, and I got $7,459.12 when I rounded to the nearest cent. So after 10 years, this is the amount of money in the account. Now, what about this other thing? How fast is this account growing at this time? The answer should be dollars per year. And to figure that out, I need to take the derivative of my function with respect to time. But since we're told that the rate at which it grows is proportional to the amount of money in the account, we already know that this derivative is equal to k times p. So we don't actually have to go through the process of taking the derivative of this function and then plugging 10 in place of t. That would be this, but it's equal to this, which is 0.04 times the function, which is 5,000, e to the 0.04t. This is the derivative of this function. I will put 10 in place of t and simplify this down to a number. Again, I'll do this in my calculator. Let's see what we get. Okay, so when I take the derivative and I evaluate it when t is equal to 10, meaning I put 10 here and multiplied this out, the number that I got, rounded to 2 decimal places, is $298.36. And the units on this, since it's a derivative, is per year. So this is the amount of money in the account. And at this time, your account is growing by this dollar amount. All right, let's try this again, but in a different example. Here we're told a culture of bacteria, it's growing at a rate proportional to its size. So I'm just going to state what that means. That means the derivative is equal to some constant times its size. And with this assumption, I know the formula has to be p is equal to p naught times e to the kt, where k is some proportionality constant. So we're told that we can assume that this is true, and I know the function for which this equation is true is this. It goes on to say the initial size is 50 bacteria cells, and after 1.5 hours, the population increased to 850 bacteria cells. Within this statement, we're actually told the initial amount. The initial amount is 50. So that was our starting point here. So in terms of setting up our equation, I know P is equal to 50 times e to the kt. The only thing that I don't know is k. If I can solve for k, I'll have an equation that models this growth. And I think that's where this other piece of information comes in. It says that after 1.5 hours, the population at that time is 850. This means if you put t is equal to 1.5 into this formula, the value that you get back for p, which is p of 1.5, is 850. I can take this information, put it into this formula. The only thing I won't know is k, meaning I can solve for it. So let's do that. I want to find k. So in place of p, I'll put 850. My initial value is 50, and that's e to the, and if I put 1.5 in place of t, I get 1.5 times k. I want to take this equation and solve for k. I'll first divide both sides by 50. So 850 divided by 50, 17. And that's equal to e to the 1.5k. If you want to remove this from your exponent, you can take a log of both sides, and it makes sense to use the natural log. And the reason for that is the natural log and e are inverses. They cancel just to give you 1.5k. And if you want to get k by itself, you can divide both sides by 1.5. And this gives us the natural log of 17 divided by 1.5 is equal to k. This, if I place it here, completes the formula for me. Let's see what the question wants us to find. If we assume that this is always true, that this rate of growth continues, what will the population be after 7 hours? So here, I'm going to set up my formula. My completed formula is P is equal to 50 times e to the, and I'll write this as the natural log of 17 times t all divided by 1.5. I can now do this directly in my calculator. I'll put 7 in place of t and simplify this, and let's see what we get. All right, well, I get a lot, and I'm going to round it to the nearest whole number since we're talking about individual cells. So the value that I get is 27609909. So after 1.5 hours, it went from 50 to 850. But then when we went up to 7 hours, it was this number, which is huge. So that's like 27 million approximately. Okay. How fast is the culture of bacteria growing at this time? That is the derivative of this function evaluated at 7. So we want to know, what is dp dt if I put 7 into that function? Well, I know this is equal to k times p, and we figured out that k is the natural log of 17 divided by 1.5, and the value of the function p at 7 is this number here. So I'm just going to copy it down and say 27,609,909. So again, the derivative is the same thing as k times p. I know k, and I know p at 7. So I'm going to do this in my calculator too. Okay, the value that I got, dp dt, evaluated at 7, is, I get 52149,841. So it's growing at a rate of 52 million bacteria at that time, which is pretty fast. So I'll label this as cells per hour, and then this one was just cells. And there is a last part. It says, when will the population reach just 250,000 cells? Okay, so I have the formula. We evaluated at 7 hours, as well as how fast it was growing at 7 hours. I think I'll put some space up here for this problem. So for this last part, we want to know, what is the value of time that would give us 250,000 as our answer? I'm going to take this number, I'll put it in place of p, and then solve for t. So we get 250,000 is equal to 50 times e to the natural log of 17 times t over 1.5. I'll divide both sides by 50. So 250,000 divided by 50 is 5,000. I'll then take the natural log of both sides. I get the natural log of 5,000 is equal to the natural log of 17t over 1.5. So here, I apply the natural log to both sides, and I got the natural log of 5,000. The natural log and e canceled to give us only the exponent left over. I will multiply 1.5 to this side, and I'll divide by the natural log of 17. And this gives me t is equal to, so that's 1.5 times the natural log of 5,000, all divided by the natural log of 17. I will round the answer for time. See what we get. Rounded to 1 decimal point, I get 4.5, in this case, hours. So we can answer a lot of questions once we get this formula, and one of those is using a derivative to figure out a rate of change. In example 3, we're told that in 1950, the world population was about 2.5 million, or it could be expressed as 2,560 million people. But then, by 1960, it increased to this population, over 3 billion, or 3,040 million. Let's assume that the rate of growth in population is proportional to the number of people. And again, what does that mean? It means that dp dt is equal to some constant k times p, or said another way, we are talking about exponential growth, meaning we can use this equation to model it. I'd like to use these two data points to figure out or predict what the world population will be in the year 2025, and also how fast is the population growing at this time. So to start with, we have to decide, well, what's our initial amount, and then how can I solve for k? I'm going to use this as my initial amount here. That is, in 1950, the population was, I'll just put 2,560, and here we're talking about millions of people. This will be time is equal to 0, meaning this value here is going to be my initial amount. And if I put this information into my equation, I get that p is equal to 2,560 times e to the kt. The only thing I don't know is the proportionality constant, k. To figure that out, I can use this other data point. That is, by 1960, it increased to this number of people. So what value of t is that going to be? That is, t is equal to 10. If this corresponds to 1950, then this will correspond to 1960. And the number of people at that time was 3,040 million people. I'm going to take this information, put it into this equation, so that means this number goes here, 10 goes here, and the only thing that I won't know is k. So I'll put that work down here. We're going to find k. So I'll put 3040 in place of p. I'll have 2,560 times e to the, and if I put 10 in place of t, I get 10k. I'm first going to divide both sides by 2,560, so I'm getting my calculator out. 3040 divided by 2,560. I get a decimal. That's not really a problem. I get 1.1875 is equal to e to the 10k, and I'll now take the natural log of both sides. And in doing so, the left side is a number, and the right side is just 10k. To solve for k, I can divide both sides by 10. So it's the natural log of 1.1875 all over 10. And it's this value that I'll put right here. And I have my function. P is equal to 2,560 times e to the, I'll write this as the natural log of 1.1875 t divided by 10. let's use this equation to predict the population in the year 2025. Well, in the year 2025, t is going to be equal to, all right, well, I'm going to take 2025 and I'll subtract 1950, and that difference is going to be my value of t. So here, t in this case, if we take 2025 and subtract 1950, we get 75. Just like here, to get 10, you would take 1960 and subtract 1950. All right. If I take that value of 75 and I put it into this formula, I'm going to do this directly in my calculator. All right, I'll round a little bit here, but I get 9,289 approximately, and that is million people. Or if you prefer, it's about, roughly 9.3 billion people. And let's see. Okay, well, that's this part of the problem. How fast is the population growing at this time? So to figure that out, we can use this idea up here. That is, we want to know, make a little space for it, we want to know dp/dt when evaluated for 75 for t. Basically, we can take this number and multiply it by k, which is this number here. So that is, I know k, it's the natural log of 1.1875 divided by 10 times 9,289. And when I do the math out in my calculator, I get 160, and this is people, million people, so let me be careful there. 160 million people per year. So that is how fast we're growing at this moment in time. 160 million people every single year. Now, there's one other part to this problem that says also, what is the growth rate? Again, kind of running out of space. I'll try to place that up here. The growth rate. So the growth rate is actually your proportionality constant, which is k. K is equal to the natural log of 1.1875 all over 10. And just to get a decimal for that, again, I'm putting this into my calculator. The natural log of 1.1875 all divided by 10 is 0.017, and I'll say 2. I'll round out to 4 decimal places. This is the growth rate. And you can actually think of this as a percentage. So you could move it over 2 places and you get 1.72%. So we're growing at this percentage, the growth rate, at this moment in time. In our last example, let's look at something that is decaying instead of growing. So here in example 4, suppose you have a 100 milligram sample of radium-226. It is known that radium-226 decays exponentially, that is, at a rate proportional to its size, with a half-life of 1,590 years. I'd like to find Q, or Q of T, the amount of radium remaining after some number of years, which I'm calling T. So for this problem, we're not using P, we're using the letter Q, I guess for quantity. But we're told that dQ dt is equal to some constant K times Q. That is, the rate at which the quantity is decreasing or decaying is proportional to the amount of stuff there is at some given time. Or, again, said another way, Q is equal to some initial amount times e to the kt. It's an exponential function that models this. Here, k is not going to be positive, instead it will be negative. So first, what is the initial amount? Well, that's the 100 milligram sample that we are starting with. This means our function q is equal to 100 times e to the kt. To complete the formula, I have to figure out what k is equal to. And I think that's where this other piece of information will come in. It says that the half-life is this number of years. What does this mean? If you put 0 into the formula, you get 100 back. Now, if you were to put 1,590 years into this, half of the substance should be remaining, which is 50. This translates into this as a point on our equation, but this will allow us to put something in place of Q and T so we can solve for K. So let's do that next. Let's find K. All right, so what I'll do is take my equation, I'll put 50 in place of Q, and 1,590 in place of T. And K is left over. I'll divide both sides by 100. I'll take the natural log of both sides. And I'll divide both sides by 1,590. And this gives me that K is equal to the natural log of 0.5 divided by 1,590. Fantastic. We now have our formula. The formula Q is equal to the initial amount times e to K, which is, I'll put the natural log of 0.5 times T, all divided by 1,590. So what is Q of 1,000? So that is after 1,000 years, how much of this 100 milligram substance will be remaining? This is easy to get. We can simply take 1,000, put it into our formula, and get a number back. And I'll do this directly in my calculator. All right, I'll round this out to 1 decimal point, but I get 64.7, and that's milligrams. And I was expecting that. This is less than the half-life. So here I've more than half remaining, so at least the number in my formula does make sense. Okay. What about this, though? It says, how long until only 1 milligram of this initial 100 amount is remaining? To do that, this is the question we're asking. We're asking, well, what do I put in place of T so I get 1 back for the number of milligrams? Let's put this into our equation. I'll put 1 in place of Q, and then I'll leave T alone, and T is the thing I'm solving for. I'll divide by 100, I'll take the natural log of both sides, and solve for T. So we have this. We have 1 over 100, which that's 0.001, is equal to e to the natural log of 0.5 t divided by 1,590. Taking the natural log of both sides gives me this. I will multiply the 1,590 to the other side and divide by the natural log of 0.5, which will solve for t. T is equal to, I multiply both sides by 1,590. The natural log of 0.01 was already there, and I'm dividing by the natural log of 0.5. That's the exact number. I'm going to type this into my calculator to see what number this is. All right, if I round to the nearest year, I get 10,564 years. So that is how long it will take to reduce this initial 100 milligram sample down to simply 1 milligram. And that's it for this problem.